Hello and welcome to our first discussions about stability, which is a fundamental requirement of all controlled systems in your control systems course and also in your career. So as an overview of today's talk, in the video we're going to talk about three things. The first is introducing what stable and unstable even means and taking a little bit of a look at how it manifests in certain engineering systems. Then talk about why stability is important. Why do we as control engineers need to understand this concept? And in the beginning, we're going to talk fairly informally, and towards the end of the video, I want to give us a mathematical framework we can use as a starting point for the remainder of our discussion about stability. So we're going to get a little bit more formal. Then in the lecture, we're going to talk now specifically about linear stability. That is to say, stability of systems governed by linear, constant coefficient, ordinary differential equations. We're going to then have a really nice result about whether a linear system is stable or not. And there's actually a nice theorem that we're going to be developing towards the end of the lecture where we're going to understand how to make that decision about our linear systems. Informally, what does stability mean? And so let's assume that we have a system, it's governed by some kind of dynamics, potentially it's a differential equation, and it is at an equilibrium point. Now, by definition, at an equilibrium point, nothing is changing. So your system is not going to do anything. If you're at exactly the equilibrium point and you walk away for 1,000 years, your system will still be there. But as we know in engineering, having the system at exactly a single point that is never going to move away from is sort of a pipe dream. We're never going to get there. And so the question is, well, what happens if I now push that system a little bit away from equilibrium? And where does that push come from? Well, maybe it's a disturbance. Maybe there's a gust of wind or something, or some noise. Maybe I was never actually at equilibrium to begin with. Maybe my measurement device wasn't exactly accurate enough. So I thought I was there, but I wasn't. And so what does my system do? Well, if it's stable, then that system is going to remain close to the equilibrium point. But an unstable system is going to move away from the equilibrium point. Now, we're going to formalize this towards the end of the lecture, but it's important to understand the fundamental difference is that if I have a stable system, then I don't have my system diverging away from this nice equilibrium point that I want it to be at. So what does all of this look like? Well, let's take a look at this video, and this is something called trailer instability. So this is something that a lot of people are familiar with if they've ever pulled a weight with a car. In this case, it's a toy car because you don't want to put someone actually in the car and have it be unstable. And what we're going to see is how important it is to keep the weight in the right place in a trailer situation. And the equilibrium point we're looking for is nice straight driving. So the car itself is not going to have to be excessively controlled. And so what we're going to do is take a look at how this video plays out. And in the very beginning, the weight is in exactly the right place. And so what's happening is as he's literally poking it, we're going right back to that stable situation of constant driving. And you can see that it's actually quite a bit of movement can happen and still get back. But now when you move the weight, now suddenly we have this instability, this fluttering back and forth, moving well away from that equilibrium point, and we definitely do not want to be there. So why is stability important? Well, if you think about what your control systems are going to do, the whole point of control engineering is to make sure that they meet certain specifications. So that might be on your rise time or settling time or overshoot and so many other different specifications that your control systems have to meet. But I want you to consider what happens if you have an unstable system. Well, if your system is unstable, and let's say it's quite badly unstable, it's going off to infinity, then it doesn't really matter how quickly it does that. So if I have an unstable system, for instance, the rise time specification really has no meaning because the system is never going to get where I want it to be anyway. Similarly, the settling time, if it's going to oscillate continuously, and as we saw in that video with the trailer there, it moved back and forth and back and forth, it never really settled down once it was unstable. And so all of these other specifications really depend on the system being stable as the first step. So that's why I said that stability is a fundamental requirement for all controlled systems, because if you don't have stability, you don't have anything. And that's the first thing you need to start working towards. Okay, so is that all? Well, no, right? So I talked a lot of informal definitions there. I said, well, what happens if we push it a little bit away from our equilibrium point? How close do we need to be to the equilibrium point to consider things to be stable? And so we need to now start formalizing this a little bit more. The other thing I want you to consider is that nonlinear systems, so systems that do not obey the linear principles, they exhibit a significant number of interesting behaviors around and away from their equilibrium points. So while linear systems are in a sense much simpler, and there's a nice theorem to tell you, yes, the system is stable and it will always do the following things, nonlinear systems, we just don't have that in general. For some we do, but not for all of them. And so that's why we're going to focus our efforts today on linear systems. All the definitions I've been giving you so far have been far too imprecise to be useful to design engineers, but it's a good start. We're going to start with those ideas of we want to go and not move too far away from equilibrium. And now let's start to formalize that so we can start talking about stability in terms of engineering specifications, which is where we want to be. So let's start to formalize this, and we're going to formalize this in pieces. In this very first piece, we're just going to consider a ODE. It is a scalar ODE, there's no vectors involved, and it's governed by the following equation: y prime is f of y, and then some initial conditions, y of 0, and we're going to call it y0. Now let's presume as though we found an equilibrium point for this ODE, and we're going to call that YE, and that equilibrium point is where the derivative is 0. So if I'm at the equilibrium point and the derivative is 0, there's no way I'm going to be moving away from that equilibrium point because the derivative governs how I change, and I'm not changing, and the derivative is 0. Equivalently, in a different way of formalizing this, I have this function f of y, and I'm essentially searching for the zeros of f of y. So that's another way of saying it. So now if we imagine that we begin precisely at that equilibrium point at ye, then y of t, the time trajectory of my system, is going to be at that equilibrium point for all time. I'll never move away from it because my derivatives are non-zero. Now we can start asking ourselves a question. Okay, well now when is this equilibrium point stable? What happens if I perturb my system and I don't exactly start at the equilibrium point? I'm a little bit off. What happens? So let's talk now about the stability of an equilibrium point. And this is the formalism that we're going to use to jump off on our discussion regarding linear stability. So let us say now that we have an epsilon greater than 0, some real number, it's epsilon, and we begin with the difference between the initial condition and the equilibrium point being less than epsilon. So we're in some neighborhood of the equilibrium point. Let us now say that we can find a delta greater than 0, again, as another real number, such that the trajectory y of t minus the equilibrium point never goes above that delta. So we never move away in the absolute value sense from the equilibrium point as a maximum of delta. Then the equilibrium point is said to be stable. If we cannot find a delta, more accurately, if we can prove there is no such delta for which this is true, then the equilibrium point is unstable. Now, this is an extremely broad definition of stability, and so we're going to be tightening it up as we start adding more and more restrictions to our systems. In particular, if we have linear systems, stability in linear systems, our original definition was extremely broad. In this lecture, so once we're done this video and we're going off to the lecture and having a discussion, we're going to focus our efforts on 3 different constraints. The first is that we're assuming our system is linear. So our system obeys superposition and homogeneity. The second, we are today going to restrict our discussion to continuous time linear systems. We're also going to constrain our discussion to time invariant systems. You may have heard that as time invariant meaning constant coefficients. And finally, at the end of this, we're going to be really talking a lot about systems that are governed by differential equations. There are other types of systems, and again, we're not going to be going into them. So linear, continuous time, time invariant systems that are governed by differential equations. So I will see you in the lecture, and we'll talk about a great stability theorem that we can use for all linear systems.